Let's get started. Today we were going to have Salim give us we're going to have three things going on today. One is Rekil's presentation on a deep dive into gradient boosting, and then Salim had something on that he prepared on a new package for, I forget what it was about. Rapids. That right? That's right.
Salim can't make it today.
Yes, that's right. That's right. So instead of that presentation today, we're going to have it on Wednesday to lead off. And today I'll just be taking us into I'll just be doing more material on the Dimensionality Reduction chapter. So first, let's have a look at the schedule upcoming. So you see, we're going to be finishing Dimensionality Reduction over the next few lessons, and then the thing I wanted everybody to point out, I wanted to point this out to everyone so they'll be aware of it, that Sunday on September 6th, we're going to take a day off. It's Labor Day in the United States. So yeah, so that's a day off. And yeah, that's it. So Rekil, are you ready to go ahead and talk about gradient boosting?
Yep, I can look at
it. Okay,
it.
Let me turn over the share to you. And let's get him started.
You guys able to see my screen?
Let's see. Yeah.
Yes.
Cool. Okay. So yeah, the couple of us were kind of looking at the gradient boosting code and trying to implement it in that homemade style that Gerard presented in the book, and things were kind of not matching up. So just kind of started looking more into it, and Kaz had a code where he was able to reproduce the exact sklearn answers, and there's a great article that he had posted along with that. So I've already posted this notebook in the Slack channel underneath today's HOML event. It's in a thread. So you guys can play around with this notebook after that. So basically, yeah, just to kind of give you a quick rundown as to what we thought was happening, what actually sklearn is doing, and there are a couple of few experiments just to see what happens when you tweak learning rates around, tweak the number of estimators. So that's what we're kind of going to quickly run through. You don't pretty much really need to know any of this if you want to use the gradient boosting package. It's just that under the hood, this is what is happening. So again, going back to our parabola, we're kind of trying to fit this curve with these points. The way we were understanding was that sklearn, the way rather Gerard does it is he first fits a model to this, and then you start calculating the residuals and fitting off those residuals. But what sklearn seems to be doing is they first fit to the mean. And if you think about what is happening over there is to draw parallel with a normal decision tree or random forest, any of those, the very first node, if you were to predict any value, your best approximate, if you could just make one prediction based off that, would be calculating the mean. And that's kind of the reason I think they're doing something like that, is you first calculate the mean, and this right now is your best prediction that you could have done if you could do like just one split, let's say. Now what happens is you calculate your errors or your residuals based off this mean and your given y values, and now you start fitting off from this. So that's what, so let's fit the trees, which is basically y minus your best prediction, and your best prediction currently is just the mean value. A key thing to remember, I think, is that when you say n estimators, you're not calculating, this step of basically calculating the mean, this obviously is not an estimator. It's just like, if you want to think of it, it's like the 0th estimator. So when you say n estimator is equal to 1, you're actually fitting one tree to the residuals and adding on the mean to that. So that's what is happening over there. A quick look at how this kind of plays along with code is, You start with your n estimators, you pass in, let's say, some number of trees. And in this case, I'm passing, just 2 trees with learning rate equal to 1. So we'll mess around with the learning rate later. First, let's just keep that constant, play around with number of trees or estimators. We go ahead, do y minus your best prediction. First best prediction is going to be a mean. So you can see that, so the red points are basically your original y's. Your green is your best prediction or your estimate at this point of time. And your blue pluses are basically the residuals. So as you can see, the first one you're fitting is just the mean, get your residuals. The very next time you're trying to fit to these residuals. And this is how you can already see, like, it's already trying to make a better fit. So to look at that in terms of, like, if you were to write this down, this kind of really helped me is, if you're calculating your residuals as you go down the trees, what is happening is you have your y, which is your target. You subtract first y, the mean of that value. Second time, you're basically subtracting whatever your tree fits to this previous residual, make a prediction on that, use the LR. And then as you go down, you're basically just adding more and more trees, more and more predictions, and your LR is just multiplied constantly throughout to all of those trees. So this is basically just showing that using a Kaz's code, and if you basically pretty much play around with sklearn, you actually get the exact same answer. So it matches. And the way that is done is you run through all your trees, make a prediction, multiply it with your LR. So this gives you one part of the answer. And there's this constant y dot mean that is being added on to it. What else? This is just combining all the piece of code up together and running it again to show that this stuff works. Yeah, these are a couple of interesting ones where you can play around and see how when LR is equal to 0.1 and a low LR and certain number of estimators versus a large LR and keep changing your number of estimators, you'll kind of see how, in this case, how things are oscillating. You start with your mean, it tries to make a best fit, you get these residuals, now you try to make that best fit, and then you kind of see, like, you're oscillating between this. This is the high LR situation, which you can kind of draw parallel with the deep learning, the parabola stuff, where if your LR is too high, you just keep bouncing around. And the third part of this notebook is you can see how, if your LR is too small, or in other words, basically, if your number of trees, if you kind of increase them, you see how these dots, these green triangles, which were actually started with the mean, they start getting really fit well to the red dots. And as you keep going, that's what is happening. You're able to make a good estimate. And if you're able to make a good estimate, that basically means your residuals are very close to 0. And this kind of shows that. The last thing.
I have a question.
Yeah, sure.
Is the residual plotted with a different y-axis?
Nope.
Because the residual has to be positive and negative also, right?
Yes.
Can you scroll a bit up?
This is at 0, right?
The first one.
This one is just the mean. That's what. So here the residuals has to be just this red thing minus this green thing, right?
So there has to be some positive and some negative as well.
So this is the 0 axis.
Okay. Yeah. Okay.
So at any point of time where the red is basically higher than the green, like you're saying, you will get these values. And the moment they start dipping here, you should. But this exactly shows, like, you're just subtracting off a mean, right? So you're just shifting the curve from one side to the other side. So this one, the first figure is the kind of, in that sense, odd figure, because you're just fitting like a constant value to it, right? After that, it kind of holds sense and goes along with our intuition that as you're fitting.
Sorry, but that, I think, was the key thing that Rekle is pointing out, which, because you're on Jerome builds from kind of, when he's building up, he kind of skips this step, which confuses us into what is really happening with sklearn. And the key detail of sklearn's gradient boost is what Raquel points out, is the very first step. It explains multiple things. One, as he said, the Y mean is calculated, but it also explains another thing that Cass and Raquel and I on the Slack were confused about, which is he has identified that even if there is one estimator and you change the learning rate, it seems to change things, and it changes things because even in one estimator you still have the Y mean, and then the first tree is fitted already to the residuals subtracted of the original Y from the mean. So even if you have one tree, the LR is applied to it, which from Jeron's explanation doesn't seem to be the case. But if you really understand what Raquel is explaining here, then even the very first tree does get multiplied by LR because every tree is fit to a residual.
Is this true of gradient boosting or just the sklearn implementation of gradient
Yes,
boosting?
that's what. That's the very next thing I'm going to show. That is, if we do it the way we are thinking, it still works. It's just that gradient boost chose to implement it this way. That's what my
sklearn chose
understanding.
to.
I'm sorry, sklearn chose to implement the gradient boost this way. So yep, go ahead.
Another question. So I love how we can see this iteratively, like the model getting better and better. When you continue through, and I'm going to jump ahead a little bit, is there going to come a point where at a certain number of trees, the model passes a threshold and it's no longer the best fit, actually begins to get worse?
Overfitting is what you're looking for, right?
Mm-hmm.
Yeah. I kind of show how LR plays a role in that. How, like, if you, it's coming. Let me not jump. Sure.
I knew I was going to jump ahead.
If I do not cover that, let me know, because I surely have that somewhere, because that was a key insight that I kind of thought and I wanted to share with you guys to get some feedback.
So the only thing that we got wrong last time was this mean plus residual on that, right? Everything else is the same, right?
There were a few other changes that we made that I think where LR was being added was also a different place. Right, we were doing LR, we were doing Y minus residual and multiplying that whole thing into LR. Whereas the way sklearn does it is it does LR at this stage where you kind of multiply it into your predictions. So let's kind of look at this piece of the code. Yeah. So we were multiplying LR here, right? We were doing Y minus best pred and then multiplying LR into that. Whereas from what we were seeing that the LR basically gets multiplied at this stage.
Okay, so the next tree is fit on the entire residual and not on residual times LR like we thought.
No, it is exactly residuals times LR, right? This one is kind of tricky. Like I said, the first one is the odd one, right? Because you're doing the Y minus best pred. So that your best pred at the first time is just going to be Y dot mean.
Okay.
So actually, that's a very good point. Actually, answering Mash's question and your question, let's kind of jump into that first. So if you do what you were saying, you multiply, let us say, the first tree's prediction and directly just add on the residuals without multiplying an LR into it, soon enough, you will be fitting to the exact residuals, which basically means you will get these green dots on those red dots, which will be the situation of overfitting, right? So my understanding of adding LR over there was basically you're saying, I have this much of error, let me fit only to 20% of that error. So as I keep going down, I'm not accounting for the total error. Because if I start accounting for the total error, if you look at this formula, pretty soon this left hand, I mean, this part where you're making the prediction will become equal to this. If LR was kind of equal to 1, right? I mean, this is the very intuitive explanation for me, which kind of made sense. I don't know if you guys think it's kind of the same thing.
Yeah, I think I got it.
Okay.
So we are allowing it to fit to the entire residual, but while adding it to the total prediction, we just take LR times that prediction.
Right, but that, like you said, but when this goes back up in the loop again, your next prediction doesn't account for the whole residual though, right? Because it's only part of that residual that has come back.
No, but No, again, it would account for the whole residual, right?
Uh,
Because the model changes now. I mean, I don't know how to explain it, but it again looks at the entire residual again.
not the entire residual, right? Because you're taking only, so let's see this then. So you do y minus best prediction, you get your first residual, correct? After you get this first residual, you're fitting this. This one, let's run through this because it's just the mean situation over here. Now when you run and go to your next best prediction, it is whatever you found. So let's say this is the first iteration. So this is y dot mean plus whatever you fit, right?
So now it has not completely fit to the residual. We
Correct.
are just
It
adding a
hasn't.
part of it. Yeah.
Yeah, you're just adding a part to
Right.
it.
Got it.
And this best prediction is what you would go in and fit in the next time.
Right. But now we are calculating new residuals, right?
Correct.
So this residual is now the entire residual. It takes everything into account, right? I mean,
Okay, I see what you're saying. Right.
Yeah.
Okay.
for
Yeah.
the current
it's the
situation, it's the
language.
whole residual.
Yes.
When you start, it's the complete subtraction, but then when you fit, I mean, when you
Add it to the
add, then it's
Correct.
a fraction.
It's only a fraction.
Then again, you calculate. So Gautam's point is that when you subtract, you start with some residual, and that is the totality of the residual.
Residual. Yeah. Right. Yeah, that makes sense. The way of putting it. Yeah.
And I can see how this can avoid overfitting. Yeah.
Can you guys repeat that question again? I think I missed it, and it was a really important point.
So, Gautam, do you want to answer that question?
Go ahead. You can. Yeah.
Okay, cool. So, okay, Matt. So, Gautam's point was, what are we basically trying to fit on each iteration, right? So, once you go down the first route, you found the mean, you found the residual. What I was trying to make the point was that when you're making a prediction, you're making a prediction on just a fraction. You make a prediction and then you're using just a fraction of that prediction. For your output. But what Gautam is kind of pointing out is that when you go back up this loop again, the next time what you're trying to fit is actually the total residual. Because this best prediction has got updated, but when you take this best prediction and you use and calculate the residual, this time you're again actually getting the whole residual. Let's actually do it this way. This probably would be. So let's say you're having two values, 8 and 6. Oops. And let's say you calculate the first mean, that will be 8 plus 6, which is 14. And so let's say you get the mean to be 7. So then let us say you calculate what your residual is. So your residual in the first case, let's say we're doing 8 minus 7, 1, 6 minus 7 minus 1. Now, let's say what is our, so in this scenario, M and your best prediction happen to be the same thing. Oops.
Initially.
Yes. Now what happens is, now we're looking at this line number 10. So now your best prediction is going to be, you do or whatever your initial best prediction was, that happens to be the mean in this scenario. And you add LR times whatever your learning rate was, whatever your intermediate prediction is. So now this intermediate prediction step is what we'll have to kind of jump over, where we're saying we have fit to this residual and we are going to get some answer. So I'm going to call that fit on this 1 comma minus 1 on the previous stage. So we get some answer. So this output will be something which is avoiding your overfitting, right? Because you're not taking the whole, you're not taking your whole residual, but you're taking a fraction of that. But now when you go into the next loop, so this is like next loop, you end up with, oops. Okay. We will go with this stage. So line number 4, residual minus y minus best prediction. The key thing what Gautam was mentioning was this residual right now that we are going to calculate is going to be the whole residual. This LR really, even though it is taking only a fraction of it, so this would be 7 plus, let us say our LR is 0.5 times, let us say in the case of 8, we are taking only 1, right?
Mm-hmm.
So then now you would get something like 7.5.
Right.
This is your prediction that you made on this stage.
Mm-hmm.
But on the next loop, when you were moving ahead, you're fitting on the whole residual, which was going to be 8 minus 7.5. So the full residual is coming into picture. Does that make sense?
I think so. I think so. So as you keep going with each iteration of the loops, you're getting closer to the full residual.
Which should actually in turn lead to overfitting.
Right.
But the way you're not doing that is because every time you're making a prediction, you're ending up taking only a fraction of that.
Huh.
So that's what is kind of, I think, yeah. Did I kind of cover all the talking points, Gautam and SKR? Like, is there anything else need to be added there?
Yeah,
of course, if you keep running it, if you keep running it, yeah,
Yes.
it's going to overfit because you're going to eventually catch up and overcome that fractional addition.
Exactly. Right. Yeah. Those are, I think that's the thing. That's the weird thing I feel, especially with gradient boost, is like there are too many moving things. You can't just change one thing and expect something to happen, because if your LR is too high, even if you increase your number of trees and keep running this for a long time, there is a scenario where you will never overfit because your LR is just too big. So you cannot account for those small errors.
Yep.
Whereas if the LR is too small and you have too fewer trees, again, you'll have the same problem because you're not running down further enough. Even though your LR can account for really small changes, you're just not letting it run enough, so it's not going to fit. So both those things play. Sort of. So both those kind of play along with each other.
So the point being that, you have two variables that you need to play with, LR and the number of estimators.
Mm-hmm. Yeah. And
they
LR
both need to be landing
reasonable,
at reasonable values to get the best fit.
Got it. Thank you.
Yep. Cool. The other thing which I wanted to kind of point out, I don't know, I guess you guys are already familiar with this, is like, this is very helpful even with random forest or any of these things where you can just kind of pull out, if you do .estimators _ you can kind of say, like, if I've just used 2 estimators here, so that's why I can just index into both these individual estimators. And this is exactly how sklearn is making its prediction. So 0 is basically the first tree it fit, 1 is basically the second tree it fit. And in this scenario, we were just using 2 trees, right? Where did it go? Yeah, if I'm not wrong, yeah, this n estimator should be true. Let's see.
Rekal, I think you cheat. Yeah.
Sorry. My n estimator is okay. Let's just run through this. This was that guy. Okay, I've set an estimate somewhere. Okay, there we go. So we have 2. So that's why this will be indexing into the first tree, make a prediction on your incoming new value. And this is making a prediction on the second tree. I'm sorry, yeah, correct. Second tree for that same input value. And you're multiplying them with whatever LR you have. And you're adding your mean back on there. This is exactly what the sklearn stuff predicts, as well as what with Kaz's code also you can get the same thing, that is which we ran through the loop here. And I just think that this is really helpful. So to give you context as to where, like, let's say you fit like random forest with 10 trees, and now you're wondering how each of these trees are kind of making predictions. So it helps you calculate the mean. That is basically the same answer that random forest would give you. The other extra thing that the random forest, I think, doesn't give you is like you can calculate like standard deviations or variances. So that gives you a good estimate on how confident your prediction is. And the next thing is that you can plot those decision tree diagrams, right, for each individual tree. Again, now it starts going more than like 5, 6, 7, not practical, but still gives you an idea. You can kind of index into each tree like this and pull things up. So that is something that I wanted to share. Going back, last one that I wanted to talk to you guys about was this one. So here I'm saying fit on Y and then fit on the residuals. So basically, this is kind of going the way Jeroen explained it. The very first one is not a mean. You kind of try to fit the very first estimate itself with the tree. And what I realized is that conceptually it was the same thing. So it should work, and it seems to work. You see that the green dots are like, I mean, the green triangles are like kind of fitting around the red circle. So I still don't know why exactly they chose that over this, but both seem to kind of work. So yep, that's kind of it. I posted this notebook in there. You guys can poke holes in that, look at it, and we can discuss on Slack.
Yeah,
any questions?
What I really liked about what Rekil has done is, it explains all the observed behavior and discrepancies, which, as he explained in the last part, there's no reason why the explanation that Jeroen gave shouldn't work and the way he illustrated. But the fact is that sklearn does something different than what he points at. So that left us confused, and Rekil's work kind of resolved that discrepancy.
Yep, I think, yeah, like Kaz's code, Kaz's discussions, Srinivas, I mean, the three of us kind of, looked into this, and different things just sat in place and started making sense. So we decided we'll share it with you guys also. So, yep, are there any other questions? Or else I'll stop sharing. I've already overshot my time. Nope. All right.
Okay, thanks, Rekil.
Yep.
Let's see. I want to share all these things. Let's see. Okay, so I was also sort of a little bit puzzled by the details of adding in, of how the algorithms works and how you fold in the learning rate parameter. So I also made a notebook, and I tried to work it out on my own, just based on what Jeroen said, and so I came up with a sort of probably a exactly equivalent formulation, but it just looks a little different than what Rekil did. So first, in words, what we can say is that, let's see, make sure, am I sharing my screen now, my notebook?
Yes.
Yes.
Okay, thanks. So in a nutshell, the gradient boosting regression successively improves the regression model by adding a correction that's estimated by fitting the error in the previous model to a weak learner, and in our case, the weak learner is going to be a shallow decision tree. That's what we're doing in this chapter in Jeroen. So there's some terminology here. I'm using correction where they use residual, but it means the same thing. So in my case, I'm initializing. So I'm always fitting a target function, and the target function is always going to be a residual is going to be a correction to a model. And so I'm just inventing this terminology. And then, so the estimated correction is what is the result of my fit. So when we fit the error to a weak learner, that's going to give me an estimated correction. And in my case, and this is what Jeroen does as well, so I tried to go with what he did. He sets the initial correction to 0. So in the first step, you're just fitting directly to the data points, right? And this differs from what Rekil did because he subtracted the mean, but I think it's completely equivalent. And then at each successive boosting stage, starting at I equals 1, you compute the exact correction, which is the difference between the target function, the one you're trying to fit, and the estimated correction from the previous step, which in this case, the first step, I just initialize that correction to be 0. And so this is the exact correction, which I call CI, which is the function that you want to fit minus the correction from the last step. And then you compute a new estimated correction by fitting the exact correction with a shallow decision tree. So you're basically fitting the exact correction. And then you update the model predictions by adding, from the previous prediction, you add the correction. And then before the next step, you have to change the target function. Now, instead of trying to fit what you were fitting before, you're trying to fit the exact correction. So this is the kind of the iterative loop. So that's the thing I wanted to do. The real thing I wanted to do was to write down this algorithm so that you can just sort of sit there and stare at it and just see that it makes sense. I wanted to make sense out of it for myself. That's why I did this. So
Joseph, just a question for you. How are you actually moving away from that 0? So that CI equals Fi minus Ci minus 1, right? Your Ci minus 1 is C0, so that's going to be 0. How do you actually, when you pick 0 instead of the mean, how do you actually move away?
Yeah, F1 is the original function, is the original data. So C1 is going to be just Y. You're going to fit directly to the data. Right? And then, so C1 is the exact correction, is basically the data, and then C1, then the C1 estimate is going to be the, C1 with a hat on top, that's the estimate, is going to be you fit that data to a tree, to a shallow decision tree. Did I answer your question?
I think you did. I need to think about it a bit more. Thank you.
Yeah, so C1 is going to be F1 minus C0 minus C estimate 0. But look here, C estimate 0, we initialize that to be 0. And F1, we initialize that to be Y, the data itself. Right? So C1 is just going to be the data itself, really. And then C hat 1 is going to be the fit, the fit to that data using a shallow decision tree.
Joseph, if I may ask, does this also imply that in the implementation, the code implementation for this function, you're keeping each step in memory, or the previous step in memory?
Yeah, and I think that Rick Hills did the same thing. You are keeping your memory. Yeah, I think this is exactly equivalent to what Rick Hill did.
Yeah, I mean, the last example that I showed was exactly this, where you're not fitting on the residual, you start fitting on Y. Mm-hmm. So that's the exact same example we both are kind of sharing there.
Yeah, and this is what Jeroen, so this is the way Jeroen explained it. So anyway, so then the next step is to modify it with by adding a learning rate hyperparameter, and then the algorithm becomes the same. All you have to do is change steps 1 and 3. So instead of subtracting off the previous estimate, you have to subtract off just the portion that you used. You only used a portion of it, alpha, a number between 0 and 1. And, right. So, yeah, and then in step 3, the new model predictions are basically just the old model predictions plus a fraction of the correction, the fraction being the learning rate. And then the next step, it's the same. You just update the target function for the next fit with the exact residual. And this is the same thing that Rick Hill did.
Yeah, except the only thing which is still a puzzle is why, while we all agree it's equivalent, it's not what sklearn does. And I don't know why he chose to explain this versus actually what sklearn does. Because if you played with sklearn and then tried to match the figures as Rekel tried to do, then you'll get different figures and you won't be able to explain what sklearn does.
No, you will get the same thing. So so to illustrate this, I first generated some noisy, I needed a nonlinear function to fit, so I generated some noisy observations of the function x sine x. So the dotted lines are x sine x, and the points are the actual function values perturbed with some noise. And the noise was just unit variance, unit variance Gaussian noise. So the standard deviation of the noise is 1. I think is it 1 or is it, let's see, let me make sure what I did. The noise variance is 0.1 times x max. Yeah, it's 1. The noise variance is 1. So, okay, so this is the function that I want to fit. Actually, the points, the dots, are the data that I want to fit. Then I just implemented the algorithm that I showed you above, and I started off with a learning rate of 0.25, and then I took 25 boosting stages. Implementation is exactly the same as the algorithm that we showed, and then the gradient boosted regression model gets this model, which you can see isn't too terrible, and then I plotted. You can sort of see what happens at each stage. So I have 25 stages, and so this is the original. So actually, this is stage 1. Stage 0, there isn't a stage 0. Just as Rekil said, you're starting off with some estimate, initialized estimate, and then the boosting stages successively improve the error. What I'm showing here is the plot of the error, the root mean squared error between your model and the data. And so you can see that at boosting stage 25, I get essentially you get a pretty good you get sort of the smallest error that you would accept. I mean, if you go any further, you're going to eventually, and as Rekil showed, you're going to eventually fit all the noise, and you'll get arbitrarily close to 0 as you want, But you'll never, a good model should never fit the noise. So you should never get less than an RMS error of 1. In this case, I knew that ahead of time. So, but in a real case, you won't know what the noise in your data is. So I stopped here just when I got to a model that I think you can't really do better without fitting the noise. And then the next thing I did was I just sort of did the same thing, except plotting the successive approximations that you get from each boosting stage. So this is kind of like a rainbow colors. The first stage is this dark purple, and the 25th stage is the red. So you can see that since I started, in my case, I started with an estimate of 0, and so my first model doesn't differ very much from 0. But then successively, with every model, I get closer and closer to the actual function that I'm trying to fit. And then to Srinivas's point, I said, okay, let's now try to fit with sklearn, and I end up with pretty much the same thing. And if the plot looks very similar, the RMS prediction error looks very similar. And the only thing that remains is to actually check the differences between my predictions and the predictions from sklearn. And they're not exactly the same, but let's see. That's something weird. I didn't see that before. It's much.
Joseph, I agree that my point was that the small differences is what triggered Rekil's, because it should end up mostly the same, but it's not exactly the same. And the reason, and specifically if you just use one estimator and dive down, because of the way that you when Rekil went through his stuff, you subtract the base estimator, which is y mean. And so if you dropped it down to one estimator, then the way LR works only on the tree, which is fit on the subtraction of y minus the base estimator and not on y itself, you would kind of begin to sketch. So I agree completely that eventually either of those ought to work from the goal perspective, but it's just that the way the specifics of sklearn seem to differ. I still don't know why, as Rekil said, they chose to implement it that way. The results should largely be fine either way, but it's just in the details, they chose a particular way, which is to first do the y-mean, and then because of that, if you drop it down to one estimator, then the learning rate will have an impact, whereas in the way you implemented and the way Rachel and I originally thought it was implemented, it wouldn't, and that those differences is what caused the investigation to say, hey, what is sklearn actually doing? So either way, we get to as good a result, and that I agree.
Right. Well, there's something wrong with this notebook. I have to fix it because this last plot here should look exactly like the last plot here. I mean, sorry, the last plot with the from scratch one, which is this. It should look like this. And so I've done something wrong here, and you can see that it's kind of messing up here. When I had it right, I must have done something wrong since then, but when I had it right, when I looked at the residuals between sklearn's predictions and the model from scratch, they were much closer to 0 than this. They weren't 0, but they were like 0.03 or something like that. Yeah. So I'll have to fix this. The point is that although this doesn't show it, the from scratch model agrees very closely with sklearn's model. So I think the algorithms are pretty much the same, equivalent. And then the last thing that occurred is that what if we why are we even using gradient boosting? Why don't we just use a single deep decision tree? Much less trouble than gradient boosting, right? So I did that. And there's the fit you get from a single deep decision tree. I didn't want to go too deep because if you do, you're going to be able to fit exactly as we've seen before. So I let the decision tree only be, let's see, I think it made it a depth of 5, and that turned out to be enough to get me down to a RMS error of about 0.99, which is the same as what I got down to with 25 boosting stages. So if I go any deeper, if I make my decision tree any deeper, it's going to overfit. So I had to stop with 5 levels of 5 levels of decision tree. So then I lost something. I actually did the last thing. Let me retrieve something from I think the one on my GitHub site is correct. Hold on for a sec. Reboosting regression, this is the one. Okay, let's see. Why don't I see it? Yeah. Sorry about this. Oh, it's still, the error is still there. I'll have to fix that. And I somehow erased the code here that did the last comparison. Oh, I guess I don't need that. You can just look at this. You can just look at this. Even though the errors are the same, the RMS errors are the same, look at how this tree fits. And for example, notice how rough the fit is here, and notice how it's overfitting towards here. Now compare that to our model, and with gradient boosting, and you can see that the fit is better. So I wish I could get that in the same frame, but if you look at that, let's say just focus on this part here, and then focus on this part here, and then focus on this part here and here, and then on the over here, here. So just by eyesight, just by comparing the models by eye, you can see that. Let's, for example, look at. Sorry to keep going back and forth, but look at this, where it's actually fitting the slope here pretty well, and here too. Now let's go to our tree model, and you can see it's doing a pretty rough job of that. Sorry, this is a deep tree model. So the reason why we use gradient boosting is because it does a better job than a single decision tree. And yeah, so that's all I have for this one. Are there any questions? And I have to fix this to get to get this plot to look right, and to get the proper comparison between the sklearn predictions and the predictions of the model from scratch, because they're very small. I don't know, Reckle, did you find that when you took the difference between your model and the sklearn model, did you get actually 0?
Yes, that's what it depends on which way you go about doing that. If you calculate the mean and then start fitting the residuals, then yes, 0. It will match the exact same thing. This is like version part 2 of the notebook that I shared, the last part, where yes, it doesn't match exactly. Because you're kind of fitting different values there. So until and unless you overfit and fit each and every point, you won't get like the same output.
Right. No, but I mean, so I mean, comparing the actual fit with the actual fit from the scratch model that you built with the actual fit from the sklearn model,
those match.
Every value is exactly the same.
Yeah, the error is 0.
Okay. Yeah, and that's not the case with what I've done. It's small, but it's not exactly 0.
Right.
Yeah.
Because you're not fitting, you're changing the first step of it. But though in essence, like what we're discussing, it should do the same thing, and it is doing the same thing.
Right. Okay,
and
anyway.
Just to kind of trigger that part of the conversation was the only reason I could think of was that if you are doing it the way sklearn is doing by calculating the mean and then fitting stuff, you're only changing the scale of the numbers that you're trying to fit, right? Because initially you would have had a much larger scale, that is the scale of y. But the moment you calculate the y mean and then calculate the residuals of that, you have shrunk the scale. But the moment I say that, then the very next question is that, wait, we're fitting decision trees here and scale doesn't matter. So it doesn't make a difference, I think, if you're fitting trees. But I don't know, I've never seen gradient boosting used with, let's say, like a base estimator of a linear regression or something like that. But I think that's where kind of the difference would come into play. That was something that kind of I was thinking of.
That's interesting, yeah.
And also another comment which is interesting is, from what I recall, XGBoost, independent of sklearn, also does it this way. So there is something about subtracting the y-mean way that implementers seem to think is a better way to get at the answer, because XGBoost, which is an independent to sklearn, also does it this way from what we could tell when we poked around with the code. So,
okay, so that's interesting.
Yeah, so I don't think it's an error. It's like done by choice, intentionally.
Yeah, it's an implementation choice. The reason why is not obvious, but it seems to be a better way to do it. Otherwise, why would two independent guys choose that way versus both are equivalent, as we have said multiple times, but in implementation detail, both these algorithmic implementations tend towards first subtracting the mean and fitting the tree on the residuals, not fitting the original tree on the actual y values.
Yeah. Yeah, I mean, the algorithms are equivalent in the sense that they're the algorithms are equivalent in the sense that the only difference is that the initial estimate in the sklearn version is the mean, and the initial estimate in Jeroen's version is 0. That's the only difference in the algorithm. But yeah, so I was just trying to make sense out of this in words that I could actually look at. I wanted to write down the algorithm to be able to look at it and just make sense out of all the symbols in words, and that's what I was able to do. And I don't know, I could try to play with this and see what happens if I change the initial step to the mean. But I think it and the weird thing is to understand why it gives an exact agreement in one case and a not small, though not exact agreement in the other case. That's the puzzle that I want to think about. But anyway, that's probably enough on this, unless anybody has any other comments. Okay. Then back to chapter 8. So first, let's have a look. I want to do this a little differently because of the way, because I don't think it helps anybody to just sit here and read for a bunch of, for 40 minutes or whatever. So for this case, because there's only a few pages, and we'd like to try to, so I'd like to try to just sort of go over this material with you and explain everything in words, and then I'm going to go to the notebook and try to go through that. So, so he's talking about a couple of different approaches to dimensionality reduction, and we're going to only look at two methods in this chapter. One is PCA, Principal Components Analysis, and the other one is, I think it's called LLE, Locally Linear Embedding. So that will be towards the end of the chapter. But right now, we're going to look at the projection way. And wait, let me make sure there's nothing else. We kind of went over all this dimensionality reduction last time, and that took a long time, even though it was only like one page. But we were able to reproduce all the things he said in code. So, for example, well, when he goes here and says that the average distance in a million dimensional hypercube is 408.25, you can verify that for yourself. If you have the random point on a unit square, if you take a random point on the unit square, it will have a 0.4% chance of being located within 0.001 from the border. You can verify that for yourself too. Let me see. I wrote a little. I think I put this on the Slack group. I'm not sure. Let's see. Yeah, cursive dimensionality. So I just wanted to verify these things, and I started doing this in class, and it turns out it's fine. I just extended it to units, to looking at the fraction of points near the edge of a unit segment, a unit square, and a unit cube. And so I was able to verify Jeroen's statement. And also, this is what we did in class. And you can also actually scale it up and do it for a three-dimensional hypercube. So I did that. I think we did all this in class. And then he makes a claim that the average distance between 2 points on a unit square is 0.52. And the distance between the points on a unit cube is 0.66, and the distance between points on the average distance between 2 points on a million dimensional unit hypercube is 408.25. So you can write this in code also, and this is the I included the segment, the line segment as well, and it turns out to be 0.33 for a line segment. For a square is 0.52, for a cube is 0.66, and then because of the code I was doing, I had to refactor it in order to do a million dimensional hypercube, because otherwise I would just have to keep typing in this a million times. So I refactored the code and did it for the million dimensional hypercube, and I got 408.25. And then that's where I ended on this little notebook. So you can look at this and verify what Jeroen said in that little 2-page section. And now let's go back to, let's see, where was I? Back to the PCA part. Okay, so the first thing that he does is he generates a bunch of data it's kind of in an ellipse, and it's kind of like only 3/4 of the way around the ellipse, as you can see here, and he perturbs it with noise, and then he plots the sort of the projection of the plane that contains that data. So this is a 3-dimensional plot, but then he projects it down onto x1 and x2, and I think these are improperly labeled. This should be x1 and x2, these axes. Let's see. Yeah, and so so that's fine. So the idea for PCA is that you would you get the data in, you'd mathematically find this plane, and then it's not incorrect. It is projected onto the plane. So you find this z-plane mathematically, and then you project the data down onto the plane, as he shows with these little arrows. Some of the points are above the plane, they get projected downwards. The points that are below the plane, they get projected upward. And so this he's calling the z-plane. You mathematically find the z-plane, and then you can project that data onto the z-plane. And then he goes to another example, and he says, and there's this example that's, I guess, built into Python. You can get it. It's called a Swiss roll. And so it's a three-dimensional sort of spirally kind of thing. And the color of the points represent some kind of an amplitude or something. It's coded. So I'm not sure whether black represents a high value. I think, I'm not sure whether black is a high value and it goes down to yellow being the zero, the low value. But I think that's the way it is. So, so then here's the three-dimensional Swiss roll, and then here's what happens if you project it down onto just the XY plane. And you can see that if you squish everything down onto the XY plane, you have a mixture of yellow, you have mostly yellow points over here, but then you have a mixture of all the different colors in the middle section, and then you have mostly red and orange points on the left. And then another kind of projection he does is he unrolls the plane, he unrolls the Swiss roll, and what you're looking at here is this should be x2, this should be labeled x2, it's the x2 direction, and this is the z direction, which is the color, the numbers that are being encoded by the colors. So I guess I was wrong. It's the black points are small values of z, and the yellow points are large values of z. So this is another way of looking at that Swiss roll in another way of projecting it. And here, nothing is overlapping. Okay. Then he looks at it in another way by separating the points into those points that are, I think, larger than 5, and he's got some boundary here, and he chooses points that are lower than the boundary and points that are above the boundary. He says x1 equals 5. So the decision boundary is x1 equals 5, which is this line. Yeah, here. So this is the decision boundary, and he says, okay, let's call all the points to the right of this line, we'll call those the positive class, and all the points to the left are the negative class. And then he just plots this thing and color labels those points. Now, instead of color labeling the points with their values of z, he just color labels them with their values of whether plus or minus, and then plus is green and yellow is minus, the minus class. Okay, so this is one way of looking at it. Now this is x1 versus x2 and x3. I'm not sure what he did. Okay, so if you look at this, this way of making a decision boundary, and then you can plot, again, this is the z, he doesn't label it, but it is, it's the z direction, which is, remember, it's the amplitude of these points, right? Like here, the high values of z are yellow in this plot, and the low values are black. He's showing the same plot here. Sorry, here. And this shows that you've got a decision boundary that actually cleanly separates the points. Then, if you look at them projected into the z direction, then he says, let's make a different decision boundary. I believe, let's see, x1. In this one, I think he takes x2 as less than 5. He uses the decision boundary of x2 as less than 5 and greater than 5. And in this one, it's the decision boundaries on x1. That's what defines these two different sets of points. Right, Srinivas, got a question?
Yeah, I was going to say, aren't the points different that he chooses between, while the role is similar? I thought that the color of the points here versus in the previous role shows that he's choosing different points.
Yes, right? In the first case, he's choosing, the decision boundary is x2 equals 5, right? So it's this line, it's sort of the plane going up from x2 equals 5. And that slices, you can see that slices the roll in some way in a vertical direction, right?
Right.
Yeah, and so when you slice it that way, you get a clean decision boundary. But when you slice it another way, with the decision boundary being x1 equals 5, and that's what this is the decision boundary. This screen here, this blue screen plot. So this is one way of slicing the data, the first row of plots. And the second way of slicing the data is choosing the decision boundary to be this vertical plane. And then when you make the same plot, it doesn't cleanly separate the 2 points. That is, plotting Z1 versus Z2 doesn't separate the 2 points, the two decision classes cleanly. So that's what he's showing here. Next, he goes into PCA, what PCA is actually trying to do. And the first thing he does is he generates a bunch of data. And I think now I'm going to go into the notebook. Let's see.
Joseph, is it okay if we read these first? Because I think it'll be better. We'll understand it better, and we'll be able to ask questions.
Okay, you like to just read those pages?
I mean, yeah,
okay.
if it's okay with everyone.
Yeah, that's fine with me. So let's look at the pages going from. Let's see. Let's look at the pages going from. I got to get my book because, well, you guys mostly have the Kindle. So let me mark those pages that we want to look at. So going from this projection section through manifold learning section, through PCA preserving the variance, and principal components, projecting down to Z directions and using scikit-learn, all the way through explained variance ratio. Let's read those pieces. Let's read those parts. And if you have the paper book, then let's see. Let me find those pages. If you have the paper book, it's going to be pages 215 through 223. So actually go through all of that, including choosing the right number of dimensions. I said, yeah, let's include this last section, choosing the right number of dimensions. And let's spend half an hour doing that, and then we can get back and discuss. Everybody okay on that? Okay.
Do you want to set a time?
Yeah, 11:08. Sorry, 11:38. We'll get back together. Okay.
Thank you.
Sound check. How long are we reading up till?
Till 11:38. All right, I guess we should start our discussion. So let's see, am I sharing this the notebook from chapter 8?
Yep, you
okay, great. So I think I wanted to move to the notebook because I thought some of his figures weren't as descriptive as they could be, so I tried to remake them, just a little bit of annotation. Okay, so let's see. I guess the first thing we can do is go through this example of PCA using SVD decomposition. So SVD decomposition is a really powerful technique of matrix factorization, where you factor a matrix into the product of a orthogonal matrix times a diagonal matrix times another orthogonal matrix, and they're usually called U, S, and V transpose. That's what this little t is. That matrix, for reasons that we won't go into here, the matrix that we want to call the matrix V, but the thing that appears that comes out of SVD, out of the SVD algorithm, is actually the transpose of V. So the first thing to know is that whenever you do SVD on a matrix, or PCA, which is almost equivalent to SVD, you have to center the matrix, that is, subtract the mean. So that's the first step. He built a whole bunch of data. He simulated a whole bunch of data. Let's see. We saw this. Let's see.
Why don't we just call that normalizing?
It's not the same as normalizing. Normalizing means you're dividing by something.
You divide by the variance, don't you, in normalizing?
Yeah. Yes. And this is just centering it. You're centering it on the mean, right? When you subtract the mean from something, that means that it's equally distributed on both sides of the mean. So it's centered on the mean.
Sorry, you don't divide by the variance, you divide by the standard deviation. Yeah.
That's correct. Yeah. So that's when you're doing standardizing, right? But here we're not doing standardizing. We're just doing centering, subtracting the mean, which is the first step in standardizing. So this is how you call the function for singular value decomposition from NumPy. It's in the linear algebra package, and you get out these matrices. Then he defines these things C1 and C2. These are the columns of VT, which are the same as the rows of V. Right, the columns of a matrix is the same as the rows of its transpose. See, okay. S, remember, is a diagonal matrix, and you can actually look at it. Let's see if we do this. We can just look at S. Oops, that's too big. Let's see. Yeah, it's actually not going to be diagonal in this case. It's going to be, let's see. First, let's look at the dimensions of it. Let's look at the dimensions of these things, which are of interest in themselves. Okay, remember the shape of X. Let's get that first, just for comparison. So he generated. Oh, I've gone ahead in the notebook, so I have to redo these things. M is 60 points. I think he just does 60 points. So yeah. So the data looks like it has 60 points and it has 3 features: X, Y, and Z. Then let's see. I wanted to look at S. So below S. And there is the so S is basically it comes out in just the diagonal elements. It's not going to show you the whole matrix, but it's basically a diagonal matrix built from these elements, and these are the principal values of the function of the data, the principal components of the data. And you can see that they're already sorted for you. It comes out from the algorithm that way: the biggest, next biggest, and smallest in order, like that. X-centered. Okay, and now if we compare the original matrix with what came out of the singular value decomposition, and I didn't like the way he expressed the matrix multiplication. There's a simpler way that's built into NumPy, and it's just U with an @ sign. To multiply 2 matrices together, you just use the @ sign, and that's all you're doing. You're multiplying U, S, and V transpose. And so this little function tests to see if they're very close to each other. And they are. So the function is completely reconstructed by its singular value decomposition. And then I guess this is what I already did, but this is the shapes of all the matrices that come out. This is the data that went in. This is the orthogonal matrix U. And this is the diagonal matrix S. Capital S, I guess he made it into a, yeah, let's see, yeah, X-centered, what? Okay, hold on for a sec. S dot shape is, okay, so X is 60 by 3, U is 60 by 60, S, capital S is 60 by 3, and all it is right now is a bunch of zeros with the 3 values inserted in their diagonal positions. So it's a big matrix of 60 by 3, but only the first 3 by 3 submatrix of that is a diagonal matrix, and the rest of it is all zeros, as we'll see in a moment. And then the other side, the other matrix V is also 3 by 3. We can look at the matrices for a moment. It might help. So, well, let's look at, since these are small, we can look at VT. And the columns of these, the rows of VT are orthogonal, I believe. Well, let's make sure. VT of 0. Well, I can do a dot product. np dot. It's either the rows or the column. I want to make sure. Wait a minute. I guess I just have to do v of 0 star v of 0, and that should give me the dot product of the first row. Oops, vt, sorry, vt. Okay, so that's not right. So then I want vt of the first column with itself. And then that should give me 1. Well, I'm sorry, I want to sum these things. So let's see, np.sum. I'm trying to show that the columns are, it's either the columns or the rows.
Shouldn't you multiply the first and the second?
No, I'm trying to find, I should make clear what I'm trying to do. I'm trying to show that this is an orthogonal matrix.
Right,
and
then
so,
you should take the first row and dot it with the second row, right? Or the first column and then the second column.
No, because that'll be 0, right, in an orthogonal matrix. If I take the dot product of the first column with itself, then that should be 1, and it is. If I take the dot product, since this is an orthogonal matrix, then if I take the dot product, sorry, like you suggested.
Yeah, I thought that's what you're trying to show, that it's
0. Yeah, you're right. And if you take, so there's 2 things that have to be true. First is that the dot product of any column with itself is 1, and I've demonstrated that for the first column. And then the other thing, as you say, is that the sorry, I want to insert the dot product of a column with another column is going to be 0, right? So if I did this, what you were suggesting, then we would see 0. So let's take the dot product of the first with the second, and that's 0. And then if I take the dot product of the next one, the first with the third column, then I should also get 0. Right, and you can run, and you can run through all the combinations, right? So the point is that the columns of VT are orthogonal, and the same thing is true of the columns of U. So let's demonstrate that really quickly. So if I do,
so these are just not orthogonal; they're orthonormal, right?
That's right. They're orthogonal. They're orthogonal and they're orthonormal. And well, orthogonal means that the rows and columns are that columns are perpendicular to each other, and orthonormal means that the norm of any of the columns is 1. So we should say that so orthogonal is a subset of orthonormal. So the best way to describe it is to say it's an orthonormal matrix. Is that your point, Rekil? Yeah. So right. So now we should do the same thing with U, and we should find.
In U, shouldn't it be the rows?
It might be. That's what I want to find out. I can't remember whether it's the columns in both or the rows in one and columns in the other.
I think because we transposed
so
it.
It's the columns in both cases, I believe.
Okay.
So let me just verify that. Insert
columns of U
below. Columns of U and the columns of V are the ones that are orthonormal.
Columns of V or columns
of VT?
Yep. Columns of VT, that's right. The columns of U and the columns of VT are both orthonormal. So yeah. So this shows that the two successive, or that a column is a unit vector. That's what this shows. And I could do the same thing with the second and with the 0 to the, you can just do it for all the other columns. Just want to insert a cell below and look at the first column, and it's also a unit vector, and you can do the same thing with the third column. So that's just sort of seeing what we have. Now here we're keeping the first 2 rows of V. That's what this is doing. This V transpose. Sorry. First 2 columns. First 2 columns of V transpose, which is the same as the first 2 rows of V. That's what W2 is. And then this is the same thing. See, this is his notation when he multiplies matrices together, but you can do the same thing, and I think it's a much more straightforward way of doing it by using the @ sign for matrix multiplication. So it's the same thing. You can do it that way. Anyway, so x2d is, so basically it's just taking the data, the first, the centered data, and then taking the dot product with the first two rows of the first two columns of V transpose, and that basically projects it to 2 dimensions. It was 3 dimensions. It just keeps 2 of the dimensions. So that's all that it's doing. Okay, so now sklearn's implementation of PCA is just called PCA, and if you can ask for the number of components that you want that you want it to return, and the maximum number is just the number of features in your data. So in this case, the maximum number of components you could return is 3, and if you gave it no input, it would return all 3 components. But if you ask for the 2 components, then it gives you just the 2 principal components, and then we can just look at them. The first few, there are 60. There are 60 entries, but we're just going to look at the first 5. This is what they look like, and you notice that they're not exactly the same. They're flipped. The sign is flipped, but other than that, they're exactly the same. Okay, and to prove that, by eye, we can see that it looks like they're exactly the negative of each other. And to prove that, we just use this little test function, and it shows that it's true. Now, to recover the full function, yeah.
What was the negative about? Like, doesn't PCA say that the sign doesn't matter? I'm just curious what happened. Why did we end up with the negatives there? Like, what caused that flip?
I'm thinking it's the implementation. It's just the implementation of PCA, okay. Because he says that sometimes it won't be flipped, sometimes it will be flipped, and so on. So it's just
again going back to
uncertain.
No difference, whatever the sign be. Both the PCAs are actually equivalent.
Yeah.
Yeah, the hyperplane defined by either of the axis things don't change if the axis flips.
Sounds good.
So PCA is in some sense an encoding of the data, and it also has a decoding function. So you can get at that by using PCA.inverse transform. So and that would be, so you encode the data, the 3-dimensional data, down to 2 dimensions. That's what we just did from the first part. We did PCA on the data, and then we that basically mapped it. Since we specified we only wanted 2 components, we've basically mapped this 3-dimensional data into 2 dimensions. And what it turns out, why did we do that? Well, we wanted, as we'll see later, we mapped it to the 2 dimensions that best approximate the original data set. So this is sort of, in some sense, an approximation of the original data set, but only using 2 components, so it won't be exact. And then once you get the approximation, you can then try to reconstruct the original data by doing the inverse transformation, and that's what we're doing here. And you lose some information. It's not going to be, now you look at this function that compares them to see if they're close, and it fails. It says they're not close, but they're not close to within a very small number, but they're still close, as we can verify by looking at the numbers. So if you compare the first row, you can see that it is close in a sense. It's just not. I think the all close function is asking for a much closer agreement. And not all rows agree as well. Like if you look at this row, the second and third elements are sorry, the first and third elements of the second row are pretty far off comparatively. But it's still the best approximation. It's trying to recover the function as best you can with the 2-dimensional approximation that you started with. So it's interesting. Let's see, somebody had a question, I think.
Yeah, Do you know if the all close function is checking for variance? Because
no, it's just checking. I think it's just checking for differences. So let's have a look at that.
Just as a tolerance limit, so if it's greater than the tolerance limit, it will return false.
Yeah, let's just see. I think we can
do np.allClose.
Oh, sorry, np.allClose. There we go. It's got a small. I think the tolerance is what 0.001 or something.
I think it's minus.
Let's see. np.allClose with a question mark. That should tell us what it's doing. Tolerance, 10 to the minus 5. So that's when it means when it says close. But we can see that in some way this reconstructed function is close, but in a different sense. It's not to within 10 to the minus 5, but it's still not too bad. So look at the third row. That's pretty good. Anyway, and you can actually get the mean reconstruction error by let's see, why would we want to take the mean? We would want np.square. Oh, it's a square. It's the mean of the squared reconstruction error. So the sum, this gives you the sum of the squared reconstruction error, and then we take the mean of it. So it's in some sense it's the mean squared error. That's what this is. Mean squared reconstruction error. 0.01. Right. Okay. Let's see. The inverse transform in this SVD approach looks like this. SVD inverse using SVD is x2 using SVD dot. So I wrote this to myself to be shown. I need to understand why this is true. But he makes this claim that the inverse transform of the data is take the SVD and take the matrix product with the first two rows of the V transform matrix, the V transpose matrix. Sorry. Remember, this is the third piece that came out of the SVD. SVD gives you a product of U, S, and V, V transpose, and this is the third matrix. So I just put this note to myself that we would like to show why this is true. So we'll probably come back to that in the next lesson.
Hey, Joe?
Yeah.
Can I just interject two things? You know,
sure.
There are a number of people on the channel that are discussing the unit vectors in VT, and all I think it really means is like, do you describe the plane, which is the same plane, like going left to right or right to left? It doesn't matter. It's the same plane, and that's the reason for the sign flip. So it's like non sequitur. It's think of it as an absolute value. It's just it's in there. Don't care. The other thing is that when we run the PCA in scikit-learn, it is going to give us all of the principal components if we don't specify a number. So if there's 3 features, it'll give back 3 principal components. 5 features, 5 principal components. It's not actually going to give us the dimensionality reduction until we force it to use the dimensionality reduction.
Right. And that's what we saw that appear. And I did mention that. Maybe I mentioned it. Maybe I went over it too quickly. But yeah, when you ask for PCA, if you give it no input here, see, we specified n components equals 2. And your point is that if we specified nothing, it would come back with 3 components, with three principal components. The maximum number of principal components is just the number of features. But there's no point in doing principal component analysis if you're not going to, if you're not going to reduce the dimensions. And so yeah, that's why we started with 3 components and we asked for 2. That's a good point. Okay, let me try to. I think we're supposed to be done right now, but let me just see if we can get through.
So just one more question on that, yes, Joseph.
Yes.
When we go from 3 dimensions to 2, so at 2 dimensions, we're now at we have like a linear combination of the first and the second. So we've got a linear combination of the two principal components, right? So you've got principal component 1 and principal component 2.
Yes.
And it's a combination of everything. I've never been able to figure out why so I can understand what we do with principal components, and we are reducing down the number of dimensions, and we do that by choosing the maximum variance and so on. But I've just never been able to figure out why that's actually useful to us. In that we've now mixed everything together, you can't separate anything out. Why is it useful to work with a lower dimension thing, even though it's easier to visualize?
Well, there's two things you pointed out. One is that principal components gives you dimensionality reduction. We know that. And the second thing you've pointed out is that it's now difficult to interpret the new coordinates because they're mixtures of the old coordinates. So you can't do, for example, with random forest and other decision tree methods, you can identify which features are important, and that means something, right? But if you do PCA first, then you lose all the understanding of what the different features are, and so in that sense you lose something, right? So there's a trade-off, and you're pointing it out. There's a trade-off in principal components analysis. One is that you lose information that allows you to sort of understand in words what each feature is, because it's just a jumble of all the other features, right? But the other thing, which is very valuable, don't underestimate it, is that you could be going from an extremely high dimensional problem to a low dimensional problem that's small enough that you can actually think about the dimensions. So you can imagine reducing a 10,000 dimensional problem to 10 dimensions, and that makes everything a lot easier to deal with and understand. It makes your model much smaller. So there are advantages, and it's a trade-off. Does that make sense to you, John?
Yeah, but what can you, so let's say we've got a whole lot of dimension, and we've even reduced it down to 2. So right, I can even plot it. But what can I do with those 2? Because it's a mishmash of all of the features. How does that help me?
Well, for example, if you wanted to build an encoder and you wanted to reduce your data set, if you had a 10,000 dimensional data set and you wanted to reduce it to 3 dimensions, this is how you do it. I mean, 10,000 dimensions, it might be way too much work for your processors to handle. But if you reduce it to 3 dimensions, then your processors can easily handle, your compute power can easily handle it. So, yeah, so John, you're saying that, oh, it's worthless because I don't understand what the dimensions are. But I think you should back off from that. It's not worthless. It's extremely valuable because now you can handle a problem that you couldn't handle before.
Yeah, can I interject something?
Absolutely. Yeah.
Yeah, so if you're concerned with the interpretability of the new dimensions, you need to take one more step, which is there in something called factor analysis. So PCA, the dimensions of PCA by itself may not mean much on their own, but there's an additional step called, and which comes in factor analysis. When you do that, then the dimensions correspond to some underlying structure in the whole sum of dimensions. So if you're starting with say 70 or 80 dimensions, and then you find that 3 dimensions gives you a suitable picture, then you could say that 3 dimensions are the underlying structure of those 70, 80 dimensions that you see on the surface. So to make sense of these dimensions, you have to take the next step and do what is called factor analysis.
So that's something I wasn't aware of, and that's interesting. I've heard the term factor analysis, but I didn't know that it could make sense out of, and I still don't really understand how it can make sense out of the jumbled up dimensions, that the jumbled up axes that PCA manages to get.
Yeah, it looks very surprising, but once you do it, it makes a lot of sense. So this has been a tool which has been used in social sciences. Anybody who deals with long questionnaires uses this method and is very familiar with this method called factor analysis. And there are lots and lots of books which will explain how this is done.
Yeah, if you could put up a simple, sort of an introductory reference to that on the Slack, that would be great, and we could all follow up on it.
Yeah, I used to lecture on this many years back.
Oh, great. Okay, that's excellent.
So I will see what I can find and then put up this thing. Yeah.
Okay.
The other thing I would say, John, is it does, while not directly addressing a question of the explainability of individual, let's say, as you said, reduce it to even 1 or just 2. the point is it gives you the dimension of greatest variance. Now you would still need to interpret it, and sometimes, and if you go through, for example, the FastAI course of classifying or applying PCA on movie data sets, you can stare at the data set and then look at, let's say, just the first dimension and plot kind of the largest values and the smallest values and see how they are different and slap an interpretation on it, and you could get a reasonable interpretation of possibly the first and potentially the second. But beyond that, I agree that it makes it very, very hard to give an interpretation, because at that point you're combining, even at 1 and 2 you're combining, but by looking at the extremes of each axis or the values at the extremes of the first two, you are usually able to slap an explanation on that axis, because the variance is the maximum for the first and the next highest for the next.
Yeah, the surprise for me when I saw that in Jeremy's class was that you could actually find an explanation for those derived features. You know, I mean, you know, in terms of something like a movie genre or something, and we were doing the movie database, right? And you could, and so he did PCA on the data, and he found new features basically that were linear combinations of the old features. And so in a sense, you wouldn't expect them to make any sense at all. But some of the features actually did make sense. Like, you know, you could look at the names of the movies and you could see, oh, these are all action movies or something like that, right? And so I throw up my hands when I see something like that, and I just say, it's due to the unreasonable effectiveness of mathematics. I mean,
and
it's like,
in fact,
it's just so surprising that you should get any interpretation out of that at all.
Yeah, and in fact, one of the resources, the very first resource I posted in Slack, if you look at it, it starts off with a very simple example and then tries to do PCA on it and then explain it by what you get. And that explanation can give you a way to slap explanations on larger data sets.
Yeah.
Cool. Okay, I'll take a look at that. Thank you. Thanks, both of you. I appreciate that.
Okay, so I'd like to, I know we're going over a little, but I want to go through this to get to the point, which is that PCA is actually extracting the directions, new directions, that if you project the data onto those directions, you get you get the most of the variance out of the data in order. In other words, each new direction has some accounts for some fraction of the data, of the variance in the data, some fraction of the spread in the data. And the way it works is that the more components you extract, the more of the variance you can explain. But a lot of times you can make do with a lot fewer components than you have features. And so that's what I wanted to run through here. So we have looked at doing the reconstructing the data, looking at the reconstruction error, and we can see that in this case, the mean squared reconstruction error is 0.01, which sounds pretty small, but really it's not as small as you think, because we really should be taking the square root of that, right? Because this is the mean squared error. The mean square root error is somewhat larger, right? 0.3 or something like that. But anyway, so this is the way we get the inverse transform. Remember, I told you there's a decoder built into the PCA, and this is how you can get it. You can either extract it directly from the model, which we did above, or you can get it by multiplying these two matrices together. And I made myself a note that I want to understand why that's true for next time. But meanwhile, he showed that the two reconstruction methods are not exactly identical, but they're close. Okay, so in other words, the two methods where you extract directly from the model or get it from matrix multiplication do agree with each other. Okay, so now we can actually look at the principal components. These are the rows of V transpose, and these are the directions for new axes, the two new axes. So let's see. Oh, and then he shows you can get them the same way using okay. this is extracting them directly from the model, and this is extracting them directly from SVD. So he's basically pointing out that PCA is essentially identical to, the PCA model is essentially identical to SVD, but it has a few bells and whistles on it that make things more convenient. Now let's look at the explained variance ratio, because that's another thing that comes out of PCA, of the model, PCA.explained variance ratio, and it shows you that 84% of the variance is explained by the first, data along the, by the projection of the data along the first new principal axis, and 15% of it is explained by the projection on the second axis, and all that leaves unexplained is about 1.1% of the variance. So with 2 directions out of 3, we can explain 99% of the variance of the data, and you'll see that in a minute. Let's see, when we look at the, let's see, he's got this, he actually makes a nice picture, and that's when you can start to really understand what's going on. Let's see, there, okay, so there's the data that he's generated in 3 dimensions. We started to look at that before. And there's the projection, of the data onto these new axes, right? So here are these 2 axes. These are called the principal axes. They come right out of PCA or SVD. And projecting the data along those 2 axes, now you've got a much simplified view of the data in 2 dimensions, but it contains 99% of the variance. This model explains 99% of the variance of the data, so it's almost perfect. Let's see, this is the Swiss roll thing that we looked at. I'm not sure if I want to do too much more on this. We can take up here when we start next week. But the main thing I wanted to get to today is that PCA finds new principal axes, and along which the variance of the data is, it extracts the best possible axes to approximate the data. So if you ask for one principal component, then it will give you the first one, where along this direction, where it explains. Sorry, which direction? I can't see from this one which one it is. But if you ask it for one principal axis, it will find the axis that explains the most fraction of the most variance in the data that it can. It will optimize that. And if you ask for 2 principal axes, it will find the 2 that will be orthogonal to each other, that will explain the most variance in the data, and so on, so on. So, and you can make a plot as he does down here, where I'm just going to run to this result to show you. You can make a plot of the explained variance versus the number of dimensions in the number of components that you ask for, and you'll often, there will be an elbow in the curve where you sort of get the most bang for the buck. So here it's maybe somewhere around 60 or 70 out of 400. In this case, the example had 400 features, and with looks like 65 or so features, you can explain looks like maybe 90% of the variance, or maybe 80-something% of the variance. So this is the trade-off you're making. You're losing you're losing precision on reconstructing the function, but you're reducing the number of dimensions that it takes to express the function. And then your choice is going to be made by you're going to always have a design choice. Your boss is going to tell you, well, I don't want the elbow, I want 95% of the variance to be explained. So then you would have to choose 150-something features, but you're still doing a lot better than 400, right? Yeah, so next time we're going to look at actually the problem of the MNIST data, the MNIST digit database, and we'll see how applying principal components analysis to that allows us to use a lot less than 728 dimensions to represent it. So with that, I'm going to sign off because